Hello everyone, and welcome to part 2 of the Chapter 7 notes. Here we're just going to be running through a whole bunch of example problems. I'm all set. I've got my "This is how we roll" shirt from Caltech, so I'm definitely in the mood to do some physics, and I hope you are too. I'd refer you to page 5 of your notes. So here we're going to be using ideas of work and conservation of energy to solve complex problems, such as what speed a roller coaster is traveling at a particular part of the loop. You can do this using kinematics equations, but it gets very complicated. And as you'll see, it's a lot simpler to deal with this as an energy consideration, or just looking at the energy of the roller coaster as it moves around its track. The equation that was introduced in the previous part is the work done by non-conservative forces is equal to the final kinetic energy plus the final potential energy minus the initial kinetic energy plus the initial potential energy. If you're wondering where that comes from, or if you're looking for a very simple application of that particular equation, I refer you to part 1 of the Chapter 7 notes. And for those of you keeping score at home, this is on page 5 of the notes where we're going to begin. So here's one example problem. Let's say we have a 10-kilogram sled that's starting from rest and sliding down the incline as shown. A constant frictional force of 15 newtons acts between the sled and the surface, right? First thing we want to do is define what y equals 0 is going to be. This is something that we see an awful lot, or we're going to see an awful lot as this goes on. And the thing which is nice about having this coordinate, or having this idea of a y coordinate, is that we can define it in such a way that is most convenient to us when solving the problem. So we're going to define y equals 0 as being the point where the sled has finished that 25-meter slide. We don't care if this is Mount Everest, that this thing is going to be sliding down. We don't care if this is the bottom of the bunny hill. For the purposes of this problem, any sliding that happens beyond this doesn't exist because we're not asked about it. So we say, all right, we're going to set y equals 0 at the point where the sled has slid this 25 meters. How much of a change in vertical elevation is this? So in other words, what's that? Well, you can solve that by saying that y naught equals 25 meters times sine of 30 degrees, or 12.5 meters. That comes from the angle of 30 degrees here, and because we're trying to find this here, we're going to be using the sine, right? So to find the work done by the frictional force on the sled as it moves the 25 meters down the incline, what we're going to say is work is equal to force times displacement, or in this case, work is equal to negative 15 newtons times positive 25 meters, or negative 375 joules. The work is done over a distance of 25 meters. You might be asking yourself, okay, what about other possible forces on this particular sled? And or why is this force negative and why is this work negative? Well, let's consider a free body diagram. So here we have the normal force coming off of the slope. We have the force of kinetic friction, looks like that. And then we have the force of gravity that's pointing straight down. It's also important, and I'm going to put this in a different color here, that we consider which direction displacement is happening. So your displacement vector looks like that. It's S, and you only have to believe me that that's S. Okay, that's an S. Let's pretend that's a good S. What's going on here? Well, the normal force is not doing any work because the normal force is perpendicular to the direction of motion. The frictional force, the force of kinetic friction, is doing negative work. It's directed in the exact opposite direction as the displacement vector. Gravity is going to be doing work on this sled as it moves. However, we're only asked so far to talk about the work done by the frictional force. How do we handle the work that's done by the frictional force? Well, we have work by non-conservative forces equals this formula. So final kinetic energy plus final potential energy minus initial kinetic energy plus initial potential energy. With friction, the work done by non-conservative forces is negative 375 newtons, which is what we found out here above. Why am I not talking about the work done by gravity? As I mentioned in the previous video, this expression is only concerned with non-conservative forces, and gravity is a conservative force. So the work that's being done by gravity is already accounted for by the change in gravitational potential energy. So keep that in mind. And again, the other non-conservative force that we might have to be concerned about, the normal force, is not doing any work because it is perpendicular to the displacement vector, right? So we go ahead and we plug in and we say negative 375 joules equals K final plus 0 minus 0 plus mgy. This is just the expression for the potential energy initial, and K final is, well, that's K final. What allows me to say that that's 0 and that's 0? Well, when it comes to the potential energy, because we have defined our y-coordinate, y equals 0, as being the point at which this sled has slid 25 meters down the slope, the y-coordinate when the sled reaches there is 0, meaning that the potential energy is 0. Why can I say that initial kinetic energy is 0? The slide is released from rest, or it starts from rest. This is not, a rocket sled. This is not, James Bond driving his car down a slope at a certain velocity already, and gravity is picking it up and carrying him even further. The initial kinetic energy is 0 because the initial velocity is 0, right? So with friction, we plug in the work done by the non-conservative forces. We set up this expression, which turns into negative 375 joules equals 1/2 mv sub f squared minus 10 kilograms times 9.8 meters per second squared times 12.5 meters. The 12.5 meters is the y-coordinate, which we have previously found. 9.8 meters per second squared is acceleration due to gravity, and 10 kilograms is the mass, which is given to us in the problem. So we do a little bit of rearranging. We solve this whole mass over here, and we add it to both sides. So we go ahead and do that, and we find that 850 joules is equal to 1/2 mv final squared. If we multiply both sides by 2 to get rid of this 1/2, we then know that 1700 joules is equal to 10 kilograms times velocity final squared. We make the substitution once again for mass. We go ahead and from this equation, we go ahead and solve for VF, and we find VF to be 13.0 meters per second. So this is the case where there is no friction. This is the case where there is friction. What about the case where there is no friction? So we've solved this in the case where there is friction. The final velocity is 13.0 meters per second. How about without friction? Then the work done by non-conservative forces is 0 joules. The only non-conservative force, as we'd previously established in this problem, is going to be friction. And because we're told to deal with this as though it's frictionless, there is no non-conservative force. So we go ahead and we say 0 equals this very same expression that we previously used, and we evaluate. You run through the same calculation, and you find that the final velocity is 15.7 meters per second. All right, so that's that problem. Let's have a look at work and energy along a curved path. So now consider a soccer ball which is sliding down some frictionless path here Or alternately, consider a frictionless pendulum. So there's no, rubbing or slowing down here at this fulcrum or at this sort of point upon which the pendulum is rotating. The first thing that this problem asks us to do is use the conservation of energy equation to determine how fast the ball that is dropped from a height of 6 meters will be traveling when it gets to the ground. This is something we went over in some detail in the previous lecture, and we'll just run through it very quickly here. Previously, we were doing this on the planet of easy mathematics, where g equals 10 meters per second squared. Here, we're going to do it on Earth. The work done by non-conservative forces is, once again, our handy-dandy expression, and we set that equal to 0 because we are assuming that the environment or that the system is frictionless. So there's no drag, there is no resistance from this hill, and so forth. We can also say, all right, once again, the normal force, which is this guy right here, is perpendicular to the displacement, to S here. So we don't have to worry about any contributions from the normal force. The only forces that are doing any work is the conservative force of gravity, right? So, once again, what we're allowed to say is that the potential energy at the end is going to be 0, and the kinetic energy at the beginning is going to be 0. We're interested at what happens when the ball is at a height of 0, meaning that there's no potential energy left, and we are assuming that the ball is dropped, meaning that it's not thrown, meaning that it has no initial velocity, meaning that its initial kinetic energy is 0. So we make the substitution for kinetic energy, 1/2 mv squared. We make the substitution for potential energy, which is mgh, or the height in this particular case. What we can say then is, because it's kf minus ki equals 0, we can then say kf equals ui. So sorry, kf minus ui equals 0. So kf equals ui. That's what you're seeing over here. 1/2 mv squared equals mgh. We solve for velocity, and we find that velocity is equal to the square root of 2 times g times h. We go ahead and plug in the numbers that we have. We're no longer doing this on the planet of easy math, so g in this case is 9.8 meters per second. The height is 6 meters, and we find that it is 10.8 meters per second. All right? So the notes ask you to use the conservation of energy equation to determine how fast the ball released at 6 meters on the track above will be going when it gets to the ground, or 0 meters, and to repeat for the pendulum. I think you can save yourself a lot of time here by saying that the speed will be the same in the case where you're dropping the ball, or in the case where it's going down this particular track. What allows me to say that? Well, we've already shown here that the normal force is perpendicular to the displacement, meaning that the normal force makes no contribution to the amount of work. We're told that this track is frictionless, which also means that friction is not going to be doing any work on this particular projectile as it slides. So only gravity is actually in play here. Similarly, when it comes to this pendulum, you do have the force of gravity, and I should write that in, and I should write that in black ink. You do have the force of gravity here. I'm sorry, I didn't draw that in earlier. And you also have the force of gravity here. But you also have to consider the force of tension. And you say to yourself, okay, why is the force of tension not actually contributing to the total amount of work that is done in this system or done on this ball? That has to do with the fact that the tension vector is perpendicular to the very, very small displacement vector, the ds vector, at each individual point. So that's fairly obvious here. You have ds perpendicular to t. but ds is also perpendicular to t at this point in the swing and at every single point in between. So tension is not actually going to be doing any work on this particular pendulum. You can also think of this a little bit intuitively when we were discussing circular motion or uniform circular motion, where if the string breaks, what happens is that the projectile goes out in a straight line. And that's just one indication that at each particular point, the displacement that you would see is perpendicular to the tension. It's perpendicular to the center of the circle. Again, because if the string breaks, it flies out in a straight line. So you're only looking at conservative forces actually doing work. And the only conservative force that you're looking at doing work is that of gravity. And what you can say is what forces are doing work, just to kind of run through what we'd already said. It's not friction, because we are told the track and the pendulum are frictionless. We know it's not the normal force, because the normal force is perpendicular to displacement. We know it's not the force of tension, because that is also perpendicular to the force of displacement. The only force doing work is gravity, which is a conservative force. So what we can say is that work done by non-conservative forces is equal to 0, which means we can use the same equation we did in the previous part, and that's going to give us the same result. So I'm going to go ahead and erase this marking here. You're still using the same equation, because the work done by non-conservative forces, which would be either the normal force or tension, are 0. So again, the result is going to be the same, and the speed is going to be the same, whether you're dropping this down a frictionless track or swinging it on a frictionless pendulum. So that's pretty cool. That's a great kind of advantage of these sorts of energy-based ways of approaching these problems. Right? Let's take a look at something a little more complicated. In the figure below, a small block of mass, 0.026 kilograms, can slide along a frictionless loop-to-loop with a loop radius of 10 centimeters. So we know that R here is equal to 10 centimeters, right? The block is released from rest at point P at height 5r above the bottom of the loop. So the questions are, how fast is the block moving when it gets to point Q, which is right here? How fast is the block moving when it gets to the top of the loop, which is here? And how fast is the block moving when it gets to point S? Let's first take a look at what our givens are. We know that h, this height here, is 50 centimeters, because height h equals 5r, r equals 10 centimeters. The first thing you want to do when you're dealing with this kind of problem is pick a convenient place for y equals 0. What is going to be your sort of reference height? And for part A, y equals 0 is conveniently, or most convenient, if it's going right through this point P. You say that y equals 0, right? We know that the work done by non-conservative forces is given, once again, by this handy expression, and the work done by non-conservative forces is equal to 0. The reason for that being that only gravity is in this particular system. We are neglecting the effects of friction. We know that UF, or the final potential energy, equals 0 because we're ending at the position where y equals 0. We have defined our system such that U sub F equals 0 at the point where we want it to, the point that we want it to evaluate, let me say that again. The point at which we want to evaluate the block is also the point where we're saying that y equals 0. We know that the initial kinetic energy, or K sub I, is also equal to 0 because we're starting at the top of the loop and the block is stationary. It's released from rest. So again, we are not throwing the block down this thing. It is released from the very top. It is stationary, right? So what this allows us to do is greatly simplify this expression. We know that U final is equal to 0. We know that K initial is equal to 0. And we know that 0 is equal to K final minus U initial, which then allows us to say that K final is equal to U initial. And so when we make our substitutions for what each of these things are, we see that 1/2 mv final squared equals mgy. We can cancel out these m terms here because the mass is the same in both cases. And we can then solve for vf squared. So we multiply both sides by 2. And so vf squared equals 2gy. And therefore, the final velocity is equal to the square root of 2 times g times y. We make our substitutions for what g is, which is 9.8 meters per second squared, and for what y is, which is 0.4 meters. How exactly did we get that? Well, we know that this distance here between the ground and what we're defining as y equals 0 is 10 centimeters, right? We further know that this distance right here is 50 centimeters, right? So if we're looking at this distance right here, which is what y is going to be, then it's simply 50 minus 10, or 40 centimeters. And that's equal to y. Because everything else is given in meters per second and in meters, we convert 40 centimeters into 0.40 meters, right? Then we go ahead and evaluate this expression, and we find that v final is equal to 2.8 meters per second. So that's pretty straightforward. Let's take a look at the other case that we've been asked to take a look at, which is in Part B. We are concerned with the speed of the block at the top of the loop. So first thing we do is pick a convenient place for y to equal 0. And in this case, that's the very top of the loop. Because once again, that lets us play a handy trick. We can say that the final potential energy is equal to 0, because that's how we've defined our y-coordinate. We've basically defined this point as having 0 potential energy. We know that Ki, once again, is equal to 0. All right. We know that the work done by non-conservative forces is 0 because there is no friction and there are no other forces that are relevant. Once again, the normal force is going to be perpendicular to displacement, which means that we don't care about the normal force in terms of doing work. We know that the final potential energy equals 0 because we're at a position where y equals 0, because that's how we defined it. And the initial kinetic energy is equal to 0 because we are starting at the top of the, well, this shouldn't say loop. This should say top of the ramp. You thought my handwriting was bad in real life. Anyway. K final in this case is equal to U initial. Once again, everything else in this expression is 0. We can bring the U initial, negative U initial, to the other side of the equation. We set up what our expression is. So 1/2 mv final squared is the kinetic energy equals mgy. We do the same thing we did previously, and we find that v final is equal to square root of 2gy, and we make our substitution. In this case, y is going to be equal to 30 centimeters, because we know that this height is 2r. So this is an r here, and there's another r here to the top of the loop. So this is 2r, and that's equal to 20 centimeters. We know that this height h is equal to 50 centimeters. And therefore, this height here, this distance, has got to be equal to 30 centimeters. Once again, we write that in terms of meters. So it's 0.30 meters. And we go ahead and very neatly find our final velocity, which in this case is 2.4 meters per second. So that's pretty clear. Now let's take a look at part C, where we are asked to find how fast a block is moving when it gets to point S. Once again, let's pick a convenient place for y to equal 0. And let's say that that point goes right through point S, y equals 0 in part C. You'll notice that this is at the same height as point P. So this should look very familiar. Once again, we set up our expression. We once again know that the work of non-conservative forces is 0 because there's no friction or any other non-conservative force in play here. We know that the final kinetic energy is 0 because that's how we've set it up. We know that the initial kinetic energy is equal to 0 because, again, we're starting at the top here, at the top of that. So the final kinetic energy is equal to the initial potential energy, Kf equals Ui. We plug in our expressions. We go ahead and do the same thing that we did before. Once again, this is 40 centimeters because this distance is 10 centimeters. This distance is 50 centimeters. So we're looking at 40 centimeters. And we find that the velocity, the final velocity, is equal to 2.8 meters per second. And you say, hey, wait a minute, that's the same answer as part A. And you're absolutely right. And that's the advantage, or the thing which makes conservative forces really cool. This is a kind of a spectacular example of path independence. The change in potential energy from here to here, from this height to this height, it doesn't matter how you got there, whether you dropped it in a straight line, whether you went down and up, whether you did a loop-de-loop. You could do an infinite corkscrew here. And as long as you're ending up at the same relative position, at the same point, relative to something that you've defined as y equals 0, the potential energy is going to be the same. So this is, of course, I hasten to add, only working because we don't have a force of friction here. So we're only dealing with conservative forces. But this is, again, a dramatic example of the path independence of conservative forces. All right, so one last sample problem. And this one's a little bit of a doozy, but we're going to go through it step by step. And figure it out. So let's say we're given the following frictionless system. You have some cart or some roller coaster. You have a height here. You have a loop which is 2h tall, and you're told that this system is frictionless. At the end of the frictionless system, this roller coaster is going to strike a spring, and then that spring is going to store the energy. In other words, you're going to do work on the spring, and then that spring will store that as potential energy. The first thing that this asks you to do is to demonstrate that the minimum initial velocity to keep the car on the track is the square root 3 times gh. And the second thing it's going to ask you is, if this height is 3 meters, how much does the spring compress at the end of all of this, assuming that the cart mass is 0.5 kilograms and the spring constant is 300 newtons per meter? All right, so part A. This is actually an interesting tie-in to chapter 5. And you thought you were done with circular motion. No, you weren't. The free body diagram at this point right here, right at the top of the loop, we have the normal force directed downwards. We have the weight also directed downwards, or the force of gravity directed downwards. And I have defined my axes as positive y going in this direction downwards. Okay? We know that the sum of the forces, the sum of the radial forces pointing toward the center of this circle, pointing toward the center of this loop, is equal to the normal force plus the force of gravity. We also know to satisfy centripetal motion around this circle, we know that the sum of the forces in the radial direction has to equal ma radial in order to get this to move around. So what we can then say is n plus w is equal to ma radial, and a radial is v squared over r. Again, if you will recall from chapter 5. So n plus w equals mv squared over r. So n is equal to mv squared over r minus w. However, in this case, n is equal to 0. The normal force is equal to 0. And as you'll recall from our unit on circular motion, when we're saying that this block or this cart is just barely clearing this particular loop, that means that as the thing swings to the top, it's just losing contact, or just barely losing contact with the loop. And then it continues onward and, slides down. So when you're talking about what happens when you have just enough energy so that the normal force is 0, or just enough energy so that the cart is losing contact with the rails, what that means is that the normal force is 0 in that case. Normal force being 0 being another way of saying that your cart has lost contact with the track, right? So we can rearrange this equation here as being w equals mv squared over r. And then because weight is given by mg, we can make our substitution for weight. Mg equals mv squared over r. We go ahead and plug in. We can cancel out the masses here. We rearrange, solving for v squared, and we find that v minimum, which is what we're trying to find here, is equal to the square root of g times r. So we take an r here, we multiply both sides by r, we have v squared equals g times r, so v equals the square root of gr. Right? So let's continue this particular problem. We've now figured out what the velocity is going to have to be at the very top of this loop. So where exactly is this equation going to come in? We'll see that in just a moment. You have to start asking yourself, okay, how can I make life easier for myself when I'm trying to solve this problem? First, we know that the work done by non-conservative forces is equal to 0 because only gravity is doing work. This is a frictionless system. Gravity is a conservative force. Set what you want to call y equals 0 so you have a convenient initial potential energy. So I would argue that a great place to set y equals 0 is right here, through the middle of this loop, and right where the cart is starting out, the initial hill, rather, that this thing is falling down. We're going to say that that is actually 0 potential energy. Okay. We also know from the way this problem is set up that because this is 2h and because this is h, that this distance, we know that this distance here is h. We know that this distance here is another h. The radius of this circle is h. Okay. You measure your height relative to that convenient y equals 0. So what we can now say is the initial kinetic energy, or ui, is 0 because that's how we've defined it. That's how we defined our y equals 0 as being this point at which you're starting out. 0 is equal to kf plus uf minus ki. So 0 is equal to kf plus uf minus ki. Right? We go ahead and plug in for each of those particular things. We know that kf is equal to 1/2 m times the square root of gr squared. Why do we know that? Well, we are defining our final position as being, let me see if I can make this a nice bright color. Our final position is right here, right there. That is what we're calling K final, right? And we'd previously shown in the earlier example, or when we were talking about part A, that the velocity, the minimum velocity that you need to keep going around the loop is square root, or no, I'm sorry. We had previously shown that the velocity at the top of the loop to keep this thing moving around the loop is equal to square root gr. I suggest that you back up. Well, I can go ahead and back up here. Can I? All right, so back in the previous slide, we'd shown that v minimum to keep this thing inside of the loop is equal to the square root of gr. So we make that substitution for what v is at this k final position. We know that the potential energy of the final position is equal to mgh. Why is that? Well, that's the expression for potential energy. It is also where we can get this h from is if y equals 0 here, we are h above, or a distance of h above that y equals 0 point, minus 1/2 mv naught squared. Okay, and what we're trying to do here is solve for v naught. That's our goal. That's what we're taking a look at. And what this problem has sort of implied, and what we're going to find is the case, is that this cart must be launched with some initial velocity, or must have some initial velocity, if it is going to be able to make it all the way around the loop. All right? So we know that r here is equal to h. We know that the radius of our particular circle is also equal to h, as is drawn in here. Oops. We can then rearrange, we can then rearrange to solve for v naught. So what we have is 0 equals 3/2 mgh minus 1/2 mv naught squared. Where am I getting the 3/2 mgh from? Okay, this is 1/2 m and square root of gr. R in this case equals h. And then if you square the square root, this becomes 1/2 mgh. We add to that one more mgh. From that we have 3/2 mgh minus 1/2 mv naught squared. We do a little bit of rearranging. So we move this 1/2 mv naught squared to the other side of the equation. We then multiply both sides of the equation by 2 to get rid of this 1/2 and this 3/2. So we know that mv naught squared is equal to 3 mgh. And we show that v naught is equal to the square root of 3 times m times g times h, which is what we have been asked to prove in this particular problem. Okay. So that's part A. I told you it was a doozy. Let's have a look at part B. So in part B, we are shown that h equals 3 meters. And how much does the spring compress, assuming that the car mass is 0.5 kilograms and the spring constant is 300 newtons per meter? Again, in Part B, pick y equals 0 to make life easier for yourself. And there is no law that says that because you said y equals 0 and y equals 0 is up here in the first part of the problem, that is the reference that you must always use. You are allowed to move around what y equals 0 is. Furthermore, and this is a very strange concept, you can actually have a negative gravitational potential energy. In other words, you've dug a hole and you need to do work to get that particular object out of that hole. That's an example of negative potential energy. However, I kind of don't like dealing with negative potential energy, so I try to define y equals 0 to make life easier for myself. Okay? So the easiest thing to do is y equals 0 is sort of the bottom here, the bottom of this loop, the bottom of everything. It's the point at which this cart will contact the spring. We once again can say that the work done by a non-conservative force is equal to kf plus uf minus ki plus ui equals 0. Again, there are no non-conservative forces at work here. We also know that K final is going to be 0 because in this problem, what's going to happen is that the cart is going to strike the spring is going to compress, and the cart is then going to stop. So at the very end of the day, at the very end of the problem, the kinetic energy of the cart is going to be 0 because the velocity of the cart is going to be 0. Okay? We can also say that U sub F in this case is going to be the potential energy from the spring. We are actually dealing with two conservative forces in this case. So the potential energy of gravity is being turned into first kinetic energy and finally into potential energy in the actual spring. So U sub F in this case is going to be related to the spring. All right. K sub I is found using the velocity that we found in the previous problem. So we proved that the minimum initial velocity required is square root of 3 times g times h. We can go ahead and plug that into our calculators, where g is 9.8 meters per second squared, because again, this is on Earth, and the height is 3 meters, because that's the amount of the drop that we're looking at. Right? And that's 9.4 meters per second. And U sub I is the gravitational potential energy, which is mgh, or 0.5 kilograms times 9.8 meters per second squared times 3 meters, or 14.7 joules. That's going to be the gravitational potential energy. So a couple of key things to keep in mind here is that our final kinetic energy is going to be 0 because the cart is brought to a stop. The potential energy, the final potential energy in this system is going to be contained entirely within the spring. There is an initial kinetic energy because this cart is moving at the beginning of the problem. And there is also an initial potential energy because this cart is at some height. Right? And what we want to do is, if we can solve for UF in this case, we know that UF is equal to 1/2 kx squared because that's work done on a spring. So essentially what we're trying to find here is the amount of potential energy we have at the very end. That amount of potential energy that we have at the very end is going to be equal to the amount of work that is done on the spring. If we can find the amount of work that is done on the spring, we can then find the displacement of that spring using this handy expression that U sub F equals 1/2 kx squared. We're bringing in a whole bunch of different ideas here. So feel free to take a look at this a few times, and also take a look at my review on springs, which was Chapter 6, Part 4. So if you need to brush up on how springs work, please have a look at that video. All right, so now what we can do is we have this expression and we can start plugging things in. We know that the final kinetic energy is 0. We are trying to find the final potential energy. The initial kinetic energy is 1/2 times 0.5 kilograms times 9.4 meters per second squared. That's, again, what we determined using this particular expression that we had derived, plus 14.7 joules. That is the potential energy from this cart being at a particular height. We solve for U sub f, and we find that that is 36.79 joules. We also know that U sub f is equal to 1/2 kx squared, where k is the spring constant and x is the displacement in meters. We go ahead and make our substitutions. We know that the spring constant is 300 newtons per meter. So we then find that x squared is equal to 0.245 meters squared, meaning that x is equal to plus or minus 0.495 meters. Why did I put a plus or minus there? Well, the work that you're doing on the spring could either be to compress the spring or it could be to extend the spring. Remember, there are two ways to do work on a spring. In this particular case, it's a compression of the spring. I guess if you insisted, if you had like a basket or like an arrestor hook or something, you could actually do work on the spring by extending it. But in this case, it's a compression. So in this case, you would say that the displacement is negative, x equals negative 0.495 meters, because the spring is compressed. And when we're dealing with a compression of a spring, the displacement is, by convention, negative. However, this question is asking for a magnitude of the displacement or a magnitude of the compression, so it probably would be better to use the positive form. All right, so that is our first set of practice problems on Chapter 7. And next time I'll be going over even more practice problems in a separate video. And I hope you're as excited about that as I am. Thank you very much, and I will see you next time.